Fourth day in chapter 7, and what we're going to add in today, we did the disk method for finding volume of a solid revolution. Again, remember the whole things are spinning around. This time we're going to bring in this thing that we're going to call the washer method. It's going to be a little bit different. So let me give you some background information first. So we take this shaded region that we have right here, and we revolve it around the x-axis. So you see my curvy arrow there. The issue is that this time if I go to put in that little rectangle that I was suggesting to you guys about, to kind of represent things, the problem this time is that there's this gap down here between the end of that rectangle and the axis we're revolving it around. And when we were doing disk method, we didn't have that problem. So what we have this time is we've got this gap. And the problem this time is that when you revolve this yellow rectangle that you can see around that axis, you are going to form something. If I drew it, if I turned it on its side and drew it, it would form a figure that would be something more like this, rather than the disk that we were creating when we did it before. The disk was totally solid when we were doing disk method, and we revolved it, and it made it we said a stack of quarters or a stack of pancakes or something like that. Well, this time, our stack of quarters, somebody's going to shoot a hole in the middle of. We're going to have this gap in the middle. So this time, we're going to call this the washer method. Okay, the washer method. So the washer has a gap in the middle when you take it and you revolve it. So the disk method has no middle, no carve out, so to speak. The washer method has this space that's going to cause a little bit of a problem. So here's basically what we're going to do. We're going to start with our f of x function. If you take the f of x function and you just redrew it, and you took that f of x and you revolved that around the x-axis, well, we'd use disk method in order to find that volume. We'd take our rectangle. The rectangle would go from that graph all the way down to the x-axis. When we revolve it, we'd make a disk. And if I wanted to find the volume, my volume would be pi integral from a to b, if that's what we're saying we're using, from a to b of my f of x function. That would be my radius of the disk squared with dx. That, revolving that f of x, that would make a three-dimensional solid. Well, but we don't want all that three-dimensional solid. With this particular case, when we revolve that particular region that's shaded there on the left about the x-axis, there's going to be a space in the middle of it. And we're going to have to address that space, and this is how we're going to handle that. So we're going to then take our g of x function, and we're going to revolve that. Well, if I make that picture, now I've got this g of x function going again from a to b that I'm revolving around the x-axis. And if I put my rectangle inside of that one, oops, let's use a different color. If I put my rectangle inside of that one, that green rectangle is going to be going from my curve down to the x-axis, whereas the red one that we used for f of x was going from the top curve down to the x-axis. So the length of that yellow rectangle is going to vary, but it's going to be basically the difference between the green one, or the red one and the green one. So when I look at revolving this g of x function, that's going to be another disk method. And my volume is going to be pi times the integral, again, from a to b. But this time it's g of x that we're squaring and integrating with respect to x. Well, what we're going to want, the blue one makes a three-dimensional solid. The pink one hollows out that three-dimensional solid. If we want to find the volume, we're going to take these two things. The volume that we want is going to be the difference between those two things. So there's your background on this thing that we're going to call the washer method. Now let's try to corral it a little bit. So washer method, there's your washer. Now just a quick reminder when I'm working with washer method, that when I'm kind of playing around with this, if I want to find the area of a ring like this, I would do pi times the outside radius, outside squared minus pi times the inside radius squared. And that would give me what that area is. Well, we're going to kind of do the same thing with this volume. When we go to do our volume of this figure that's formed by revolving my area about the shaded region, this time my volume, we're going to kind of do the same thing. Pi integral from your A to B, whatever your bounds are, we're going to take the outside radius and square it. And we're going to subtract from that the inside radius squared, integrated with respect to x. Now, if we're doing y's, everything would be the right radius minus the left radius, as we talked about with the disk method. So washer method, that orange thing right there, is kind of your template. Now, the tricky thing is, how do you get the outside radius figured out? Well, the outside radius, as I drew in that picture that I had up there, the outside radius would be the red. The outside radius would be the red. The inside radius, as I drew in that picture up there, would be the green. And what we're looking for is the difference between those two things. So this washer method is going to be a bit confusing for people, especially on the heels of, we're still trying to figure out disk method, but washer method, when do I use it? I use it when I look at this yellow representative rectangle I have right here. When that yellow rectangle is not attached to the axis I'm revolving it around. If it attaches itself, we use disk method. If it doesn't attach itself, we use washer method. All right, so let's try a couple problems here. First one, volume of the solid formed by revolving the region enclosed by f of x and g of x about the x-axis. So here we are. Zoom a little bit so I can have it all on one screen. So we're going about the x-axis this time. Picture, I think I can figure this one out pretty easy. So if I wanted to do this, if I wanted f of x, so square root of x would look something like this. X squared would look something like this. And if I wanted to find, and we're revolving it around the x-axis. So the region I want is the part that's enclosed by those two things. I'm going to take my yellow rectangle, I'm going to put it in. Putting my rectangle in perpendicular to the axis I'm revolving it around. And so now, is that yellow rectangle going to attach itself to the x-axis? Well, if x was equal to 0, it would. But at every other x value, it won't. So what we're saying as we look at this, there's a gap in between here. That's a bit of a problem. If there's a gap, we automatically know that we're going to use washer method. So how do I do this now? Well, so let's see. So I go to set up my integral. So I'm using washer method. So my volume, pi integral, I got to figure out the bounds. I'm going to need an outside radius. I'm going to need an inside radius. I'm going to need my dx. So what are my bounds? Well, let's figure out bounds. So in order to find your bounds, we'd set square root of x equal to x squared. We'd square both sides. X is equal to x to the fourth. Move your x over. X to the fourth minus x is equal to 0. Factor out an x. X cubed minus 1 is equal to 0. I think we're going to get x equals 0 and x equals positive 1. No negative 1 this time. So there are my bounds. So my bounds are saying let's go from 0 to 1. Got that part figured out. Now my inside radius. Fastest way, easiest way to figure this out in my mind, we're using the red and the green from above. So take your pen, that rectangle that you drew, put your pen on the furthest point away from that rectangle, the furthest point from that rectangle to the axis you're revolving it around. So from that dot that I just drew down to the x-axis. Is that distance always the same? No. It varies. What does it depend on? It depends on what f of x is. So f of x is that blue curve. So that means my outside radius is my blue f of x. Inside radius. Take your pen, put it on the closest point on that yellow rectangle down to the axis you're revolving it around. Is that distance always the same? No, it depends. What's it depend on? Well, whatever x value it is, it depends on the red curve because sometimes it's smaller and sometimes it's bigger. So that means that radius is going to have a variable in it. What is going to happen to that variable? Well, that inside radius is that red graph, which is our x squared. Now, again, I'm not going to spend a lot of time figuring out how that works with your calculator and all that other kind of fun stuff. If you put that in your calculator, you are going to end up with 3 pi's over 10. So pi times 3/10, if you want to figure it out, or 0.942, I think is to 3 decimal places, cubic units. Let's go look at number 2. So number 2, find the volume of the solid form by revolving this region, or enclosed by this function about the y-axis. So this time I just changed things. I changed the rule. This time we're going about the y-axis. If we're going about the y-axis, we're going to throw everything on its ear. So let's sketch this out. So here we are again. Y equals x squared plus 1. That would be a parabola that would be opening up. It would go through the point. It would have a vertex at the point 0, 1. Y equals 0 would be the x-axis. X equals 0 would be the y-axis. X equals 1, pardon me, x equals 1 would be this red line over here someplace. So my region, it appears, is going to be in here somewhere. Okay, so here's what's going to get tricky about that. So if I take this and I try to shade it in and do a good job shading it in, now remember, the key to all this is we're revolving this thing this time about the y-axis. So when I go to put my rectangle in, when I go to put in my rectangle right there, there's my rectangle. If I put it in that way, I'm revolving around the y-axis this time. So I got a step ahead of myself. I put my rectangle in perpendicular to that axis. Is that rectangle going to attach itself to the axis I'm revolving it around? The answer is yes, every time. So if that's the case, I'm going to be using disk method. But my problem is, if you slide that rectangle up, eventually, instead of being between the black line and the red line, it's in between the blue line and the red line. So let's do this with another yellow one. The blue line and the red line. And the bottom line here is we have a bit of a problem because one rectangle can't represent that whole thing. We're actually going to need 2. We're going to need a different rectangle for where things change. So if we need 2 rectangles, that means we're going to need 2 integrals. So my bottom rectangle has no gap in it. We're going to use disk method. So if we're using disk method, set up your template. Pi, integral from I don't know where to I don't know where, something squared. Oh wait, those rectangles are horizontal. We got to do everything in this problem in terms of y. The other rectangle, because it's in between 2 curves, there is a gap again. And if there is a gap, we know that this top rectangle is going to require us to use a washer method. So there's a gap on the top one, but not on the bottom one, which means we need 2 separate integrals. So now when we set up our washer method, pi integral from I don't know where to I don't know where, something squared minus something squared dy. All I have to do is figure those things out, and when I add these 2 integrals together, I will have what I need. So now, remember, everything in the problem, according to those integrals I have written down, is in terms of y's. So I know, let's look a little closer at that picture that I have there. I'm going to zoom this in a little bit. If we come over and we look at this picture that I have, let's label some points. So what do we know about these points? Well, this looks to be the point 0, 1. I know this is the origin. I know this is the point 1, 0. And I think if I went and checked, if I plugged x equals 1 into that blue function, I'd get the point 1, 2. So those are the corners of my region. It's always helpful to go through and label those, because right now if I'm going for y's, I see that there is a difference taking place below or above that line I just drew. Below that line, we have a disk method, and you can see it on the screen we have right here. Well, where does that integral go from? That integral goes from y equals 0 to y equals 1. And how long is that yellow rectangle? Well, it's always at least up until y equals 1, it's always the difference between the red line and the y-axis. Where's that red line? Well, that red line is exactly 1 unit from the y-axis. When I get to the other integral, when I get to that top yellow thing that I drew, this one right here, well, those distances change. This time, I'm going to need a washer method, which I already have set up, and now I'm going to need an outside radius. Well, outside radius, let's do what I did a second ago. Put a dot on the furthest point on your rectangle away from the axis you're revolving it around. What's that distance? Well, that distance, I think, is always going to be the same. What's that distance going to be? That distance, it looks like, is always going to be 1. When I go to find the inside radius, put a dot on the closest point to your rectangle from the axis you're revolving it around. Well, what is that distance? Well, that distance is going to change. That distance is going to depend on this blue function. Now, the blue function says y is equal to x squared plus 1. So I could just put x squared plus 1 in there. But wait a minute. I can't do that because everything in the problem has to be in terms of y. So I have to get this equation. In this equation, I have to solve for x. Y minus 1 equals x squared. X is equal to plus or minus the square root of the quantity y minus 1. So if it's plus or minus quantity square root of y minus 1, well, the plus side is the right and the minus side is the left. We want the distance from that blue graph over to the y-axis. That distance is the square root of y minus 1, and we only need the positive this time because we're using the right side. We're using the positive half of the graph for the x's. And the only thing I'm missing then are the bounds on that integral. And that integral, it looks like, starts at y equals 0 and goes to y equals 1 and goes to y equals 2. And if you put those into your calculator, what you're going to find is this pink one turns out to have a volume of pi, and this black one turns out to have a volume, it looks like it should be a little bit less, turns out to be a volume of pi over 2. And if you put those two things together, we end up with 3 pi over 2 cubic units. So again, the difference between when is it a disk and when is it a washer, it's a disk when there is no gap, such as this rectangle right here. It's a washer when there is a gap, such as that one right there. So there's your washer method.